The following is a selected video from masterthecontent.com, where you will find an extensive video library of lectures for a variety of standardized admission tests. We offer over 600 hours of detailed video lectures for a multitude of standardized tests. Use our interactive in-lecture table of contents to find specific topics of interest. Work through numerous in-lecture examples to help you internalize concepts. To learn more, visit masterthecontent.com. Your career, our passion.
And pretty much what we're doing here is discussing the properties of acyl halides at length. Now, acyl halides are commonly used for the synthesis of other derivatives. Now, why are they used for the synthesis of other derivatives? Because they are the most reactive of them all. So they're the most reactive of all the acid derivatives we're going to be talking about today. And because they are the most reactive, they can be used to synthesize less reactive derivatives. Okay, they can be used as a precursor to synthesize less reactive derivatives. Now, what I want us to do is briefly discuss why acyl halides are the most reactive members of this group. So we're going to look at inductive effects versus resonance. Okay, so now in an acyl chloride, for example, the halogen, which is chlorine, is a very electronegative element, and electronegative elements will tend to withdraw electron density from the carbonyl group via induction. So the process by which they do so is called induction. So just to direct your attention to that generic acyl chloride that we have on the screen, because chlorine is such an electronegative atom, it will pull or withdraw electron density away from the carbonyl carbon. So I'm talking about this carbon right here. That carbon right there. So this chlorine atom right here will pull or withdraw electron density away from that carbon in its direction. All right, now, inductive electron withdrawal in this way will actually make the area or the space around this carbonyl carbon less negative, or we can say that it will increase the partial positive charge of that carbonyl carbon because of the relative polarity of the group. So I'm going to repeat that one more time to make sure you understand it. So we have this very electronegative chloride atom, which is much more electronegative than carbon. Okay, the carbon of the carbonyl group right there. Because of that fact, it will pull or withdraw electron density away from the carbon towards itself. I'm talking about the chlorine atom. This results in the creation of what we refer to as a partial positive charge around that carbon right there, which effectively reduces the amount of electron density around it. Now, that reduced electron density makes this acyl chloride more susceptible or more prone to nucleophilic attack. And the reason as to why this is the case is very simple. Now, I want you to remember is that negative charges will repel each other. They tend to repel each other. That's a very basic concept. So if we have a lot of negative charge around that reaction center, around that carbonyl carbon, it will be very difficult for our nucleophile to come in and introduce more negative charge with its lone pair of electrons to form a new bond. So what the chloride ion in this case effectively does is that it reduces the amount of electron density around that carbon, which makes it easier for this nucleophile right here to approach and attack and add to that carbonyl group. So all in all, the degree of electrophilicity of an acid chloride, okay, the electron-loving nature of an acid chloride is in large determined by the nature of the substituent to which the acyl group is bonded. If you have a very strongly electron-withdrawing substituent, as you do in this case, it will pull electron density away from the carbon, which will increase its partial positive charge and make it easier, or make nucleophilic attack an easier process, which will effectively increase the rate of reaction. So induction, in this case, will increase the reaction rate. So we've established that. Now, let me pick your brains a little, okay? And I'm going to direct your attention to what we have to the right-hand side of the screen right there, which are the resonance forms of the generic acyl halide that we have on the screen. So as you can see right there, drawing out those resonance forms, we have two additional resonance structures in addition to the neutral one, and that's this one right here and this one right here. So all in all, we have by the depiction or by the diagram on the screen, we have 1, 2, 3 resonance contributors to the overall structure of that acyl chloride. Now, remember how electron delocalization happens. Remember how resonance happens. Because of the simple fact that these 3 atoms right here, the oxygen, the carbon, and the chlorine, have overlapping p orbitals, they can share or delocalize electrons amongst themselves. So electrons can be shared amongst themselves, which effectively distributes the negative charge across those 3 atoms, okay? And that's because of p orbital overlap. Now, if you're distributing or sharing electrons across those 3 atoms, you will almost certainly result or come across a situation where you're actually adding electron density around that carbonyl carbon, around that carbon right there. And as you can see in this resonance variant that we have at the end of the screen right here, there is what is a double bond between the carbon and the chlorine, and this positive charge has effectively been transferred to that chlorine atom right there. So as you can see, the amount of negative charge at that carbon has been increased, and that's through resonance. So if we're increasing the amount of negative charge around that reaction center, our carbon, that means that it will be harder for a nucleophile to come along and attack that reaction center, that electrophilic center. So we have a case where we're dealing with 2 competing effects. On one side we have induction, which actually increases the reactivity by inductive electron withdrawal, and on the other end we have resonance, which actually decreases reactivity by electron delocalization. These are 2 opposing effects. So if we have the resonance effect increasing the electron density around the carbonyl carbon and making it less reactive, and at the same time we have the inductive effect pulling electron density away from the carbonyl group and making it more reactive, which one of these effects is more important? Which one should we consider more closely? Which one is actually playing a larger role in the reactivity of the acyl halide? And why is it that the acyl chloride remains highly or very reactive despite the effect of resonance? Now, the answer to that question is very, very simple, and I'm going to tell you what it is. So, for delocalization to occur, you need what is called effective orbital overlap. So, p orbital overlap. So, the p orbital of oxygen, right there, needs to overlap with the p orbital of carbon, which needs to overlap with the p orbital of that chlorine atom right there, which is what allows you to actually delocalize electrons across those 3 atoms. Now, if you don't have effective orbital overlap, then you cannot effectively delocalize electrons across those atoms. Now, I'm going to direct your attention to the 3rd resonance form right there. This form right here actually does not exist. And the reason as to why it doesn't exist is very simple. Going from carbon to chlorine, we do not have much overlap of their p orbitals, okay? We do not have effective orbital overlap from carbon to chlorine. So the p orbitals of carbon and chlorine, they do not effectively overlap. What does this mean? This means that electrons cannot be shared or delocalized across those 2 atoms. So this 3rd resonance form that's formed by the delocalization of a pair of electrons from the chloride to form that double bond actually does not happen. That does not exist. So all in all, we can eliminate this 3rd resonance form because it's highly unlikely that it will exist. We can take it out of the picture, and what we are left with is 2 resonance forms as a depiction of what an acyl chloride would look like. So those are the major contributors. And as you can see in these 2 resonance forms, we do not have any new or any additional negative charge being introduced at that reaction center at our carbonyl carbon. So for this reason, resonance is not a major factor when it comes to acyl chlorides. So we're going to have induction, which will make them more reactive, which will be a very important effect. But on the other hand, resonance will not play much of an effect as far as the reactivity of acyl halides is concerned because of the simple fact that we do not have effective p orbital overlap from carbon to chlorine. So I hope that makes sense. Now,